Today we're going to talk about simulation-based engineering and for the entire life cycle of the plant. This is Andritz technology for the last 30 years in many different mining operations around the world. It's getting a lot more popularity for the last 5-6 years because of the value of the dynamic simulation and dynamic modeling. And we want to discuss that more in more details of the value proposition and what is the technology is all about. So we'll start with the IDEAS process simulator. This is Andritz proprietary fully dynamic modeling software, but adding with the dynamic modeling is also steady state modeling. Another important aspect for IDEAS simulation software is the ability to add continuous process simulation with the discrete event simulation, which allows us to actually model trucks, the mining to process all the way to the port and the shipment, all in one processing model. Also, we are able to do all the stoichiometry, particle size distribution, all based on the first principle models. And if we are not having the first principle models, then we can have a basically all empirical and semi-empirical models are also inside IDEAS. So basically what we do is that we get the PNID design, the mass balance, the layout drawing, the equipment manufacturing equipment, the data sheet, and also the process description, every information that you have. And then we start building a fully dynamic model. IDEAS is an object-oriented simulation software, and we have 40 different industrial libraries. As you can see, mining and oil sand is among them. So we have the models of all different equipments in mining, and that we can actually connect to each other with all the material properties and so on and so forth. But what is the important aspect of IDEAS and fully dynamic modeling is not just the software itself, but actually what we're going to use it for the entire life cycle of the project that you have is the important part. We can start with a feasibility study, doing a simple steady state modeling or semi-steady state modeling to show you the mass balance, the energy balance, and also the production cost, and as well as the equipment cost and also the project cost. But what becomes very important and basically differentiating factor for Andritz technology is when we get into the the detailed engineering design stage, when we get the help designing the PNIDs, and we call this PNID validation. How many times have you had the experience that the project has been built, in millions of dollars had been invested, and then when the operation starts, the process has not brought the value that was predicted? And you know, we're all engineers, we all make mistakes, and we are able to actually capture all those process mistakes or shortcomings during the PNID validation. So think about it as an insurance and also as basically something that helps you to understand, is my process, the day that I start ramping up, going to bring the values that the design was promising or not? That's what we call the PNID validation, and that's the detailed engineering stage. So before I go further, I want to show you just how the IDEAS software looks like, and what does the dynamic modeling mean. This is just a very simple model demo for a gold concentrating plant with the comminution. And as I said, this is just for the demo. But you can see we have leaching, we have the CCD, and we have the comminution area. Now, what we're going to do is we're going to look at the comminution area and look at some of the places here. So for example, the sag mill, as you can see in IDEAS, we have all the impact breakage functions, the self breakage, the attrition. We are able to look at the material properties that is coming in. We are able to look at the actually particle size distribution that is coming into the SAG mill, and then predict what are the particle size distribution of the material going outside of the SAG mill. The important part is the dynamic ability of ideas. So right now we have the ball mill and the SAG mill here. What I'm going to do is that if you look at this pump, there is a PID controller that is running at 50% level for the sump pump, and the pump is actually at the 50%. Now what I'm going to do is I'm going to decrease this. I'm going to increase that to 68%, and then as we can see that the level in the tank is starting to rise. Obviously there is a fluctuation because of the PID, and the level at some point is going to start to stabilize at 70%. While that is happening, there is a lot of action is happening on the power consumption inside the ball mill because there is circulations that is happening, and it's worth noticing that we are running the simulation 18 times faster than real time. Same scenario inside our recovery part and the autoclave. We have all the stoichiometry of the processes that is happening inside the chemical reaction is happening inside the autoclave, and then we are able to actually with this stream analyzer look at all the components that is coming inside this autoclave, and then in real time see what are the components that is going out. So you can see that fully dynamic modeling, and based on the changes that we have in the process, all these going to have effect. Now let's continue on why ideas is able to give us the high fidelity model, which is basically the how close is the model compared to reality. Is because we can have the metallurgical and process with the mechanical plus the control and the human factors all together at the same time, which is helping us to increase the accuracy of the model. At some points we were at some projects we even have modeled the human interactions and interventions inside the process because that they were relevant. So the other part of the PNID validation is because we can help it can help us to decrease the capital cost because of these cascaded contingencies that comes with the mechanical design, process design, and so on and so forth. So we can actually add these, and when we have a holistic model, we are able to look, do we really need that tank at that size, or can I actually do something with the control strategy to decrease that size of my buffer tank so that decrease the capital cost? Now, here's the interesting part. When we validate the design, then it comes to the time that we are getting ready to getting near the commissioning time. Imagine around 8 months before the commissioning time. That's the time that control system is ready, the design is ready, and instead of going into the back, like in the old days that we go into the site and start commissioning the plant one by one, and the controls strategy, you find all those problems during the commissioning time, we are able to do a complete virtual commissioning 8 months to 9 months before the actual commissioning time. So imagine that we are able to connect the models, the fully dynamic models, to the control system, the real control program, and then when we connect these together, we sit down with your team and with the engineering team, and we start commissioning the plant. This is a hot commissioning, virtual hot commissioning. And all those problems for tank overflow, things not happening, PIDs not working, all those problems, the control strategy not working, all will come out. Now, of course, we have done studies, many studies, and we found that we are able to find 82% of all the problems regarding the automation during the virtual commissioning, and the ones that we cannot find are the field problems. Those field problems, obviously, if there is something with the problem with the wiring, we cannot do it on the we cannot find that problem on the virtual stage. However, as many of you are seasoned mining engineers that were in the commissioning time, you know that majority of the time is wasted on the troubleshooting. So this helps you to know where to look for the problem. There is no, the other thing that we see every time when we go through the virtual commissioning is to find the lack of information. This is the reality. We have so many stakeholders that are working together. There's an engineering company, there's the equipment manufacturers, there's the operation and the owner, and also there's the control engineers and all that. There is a lot of times that the information has not been available. All those things will come out to the surface 8 months before the commissioning time, which helps you to deal with them before you go to the commissioning. Now, when we finish the commissioning, that's where we get to the operator training simulator, which is basically having the same setup. Now we have a software called Instructor that allows us to train the control room operators. We sit them in front of the screens that they will see the same exact screen that they will see in front of in the plant, and then they start operating the plant. This is not training the operator how to use the control system, is training the operators how to operate the plant. And then the instructor software will throw the operators into different scenarios. The ore system ore changes suddenly, and they have to change the efficiencies changes, and they see they have to detect what is going on, and then do the right action to mitigate the problem. A lot of equipment failure can happen. Basically, think about it as a flight simulator. When you want to train your pilots how to deal on all the operations problems before they actually get exposed to it in the plant. The other value here is that the operators learn how to use automation before actually going inside the plant. And this is becoming a very important topic for changing the culture of the operators to not manually control the plant and get used to those manual intervention, and instead of that, use the automation system to actually help them to have a more efficient operation. So to summarize all this, we have the operator training simulator for training the control room operator. We also have the interactive process training to train the field operators to learn how to actually do the field work and do the maintenance. We can use these technologies later on to connect to the real-time operation and build a real-time digital twin and do the optimization. Now, what does all of that mean for your project? Because at the end of the day, it has to be having a value. And this graph perfectly shows you the value from one of our customers in the past. Basically, it's all about decreasing the ramp-up time. It's all about decreasing the risk when you are going into the commissioning and starting the operation. So as you can see from this graph, the blue line is a project that one of our customers did before, and this was the ramp-up time that they had. And the red line is the plot for expectation of the ramp-up that they were trying to achieve. But then now the green line is what they got, which is basically 4 months before the planned time, they were able to achieve 80% of the operation and ramp up much faster. Think about how much value that is for your operation. We call the whole entire solution for you operational readiness. You will be ready to operate when you start commissioning, because your P&ID design and your process design is completely de-risked and is completely verified. Your control system is completely virtually commissioned, and you already commissioned the plant one time. You found all the problems that you might face. You will have a decreased commissioning time, and your operators have been trained how to operate the plants a couple of months in advance before the operation starts. And because of that, you're able to decrease the ramp-up time. Thank you very much for your time, and looking forward to talk to you soon.